Hi, I'm Prof and welcome to Chemistry Matters. And today we are going to talk about the fundamentals of acids and bases. So, those are two words that I'm sure everybody watching this has heard of, acids and bases, but what in fact do we mean by acids and bases? What are these substances in chemical terms? So, there are, just to make things complicated from the get-go, there is more than one definition of what we mean by acids and bases. And weirdly enough, they both came out in the same year, 1923, from a sum total of 3 different people. First up, there was a pair of chemists named Bronsted and Lowry, and working independently of each other, they came up with a definition of an acid that said that an acid is a proton donor. And meanwhile in the States, a guy by the name of Gilbert Newton Lewis came up with his definition of what an acid and a base was. He said that a Lewis acid was an electron pair acceptor. A Lewis base, on the other hand, is an electron pair donor. And so we've got two sort of different, I guess, definitions. Now, it turns out that the Lewis definition is the more general of the two. The Bronsted-Lowry is definitely more specific, and that's the one that we're going to be going with because we are going to be talking about acid-base behavior in water. Okay, and as we will see, protons are very, very important in water. Okay, so that's the definition that we're going to be using. An acid is a proton donor. Now, you might think that this means that we are going to be talking a lot about protons, H+. There's the formula of a proton, but in fact what we find is that if we tried to put or get a free proton in water, you wouldn't have a hope of doing that. The reason is that the free proton is incredibly polarizing, and it is going to accept any electron density that it can get hold of. And so what happens, instead of talking about H+ in water, we must really talk about H3O+, okay? And this is a thing called the hydronium ion. And in actual fact, that's not the whole story, because we can also get a proton reacting with 2 moles of water to give us H5O2+, or 3 moles of water giving us H7O3+, etc., etc., etc. But H3O+ is the predominant form of the proton in water. So whenever you see this now, think a proton reacting with water. Okay, so proton donor. An acid is a proton donor. And the one thing we didn't say about the Bronsted-Lowry theory was that a base is a proton acceptor. Now, hopefully you know enough that you know that acids react with bases, okay? And so from the Bronsted-Lowry definition of an acid and a base, we can look at the simplest, really, possible acid-base reaction, where we have H2O plus H2O in equilibrium with, and you might think, well, what does water plus water give? Surely it just gives water, it doesn't react. Yes, it does. It does react, and what you get is hydronium ion H3O plus OH minus the hydroxide ion, okay? And that, as you see, is written as an equilibrium. So this is an equilibrium process, okay? Water plus water is an equilibrium with H3O plus OH minus. Okay, so because this is an equilibrium, as we've learned in previous videos, we can write an equilibrium constant for this process. Now, this is a pure liquid. It's not going to appear in the equilibrium constant expression. Likewise, this as well, okay? So these guys are the only ones that are going to be appearing in our equilibrium constant expression. H3O+ and OH-. So we're going to write the equilibrium constant expression for this, and we're going to give it a special name. We're going to call it Kw because it is so important. And Kw then is simply going to be equal to the concentration of H3O plus, because it's an aqueous species and that goes in equilibrium constants, multiplied by OH minus concentration, and that has a value of 1.0 times 10 to the minus 14 at, all importantly, 25 degrees Celsius. Okay? And this is an incredibly important equilibrium constant, as we will see during these lectures on acids and bases. Okay? So look at the value of this, 10 to the minus 14, 10 to the power, of minus 14. Very, very small. Now, Kw refers to pure water. Okay? Pure water. What do we know about pure water? Well, we know a few things, but we know that pure water has got a pH of 7, don't we? That's one thing that most people know. Whenever they hear the word pH, they know that water has got a pH of 7. How can we show that? Well, we can show that through the stoichiometry of this reaction, okay? So we know that Kw is equal to H3O plus concentration multiplied by the OH minus concentration, 10 to the minus 14. Now, from the stoichiometry of this reaction, we know that in pure water, concentration of H3O plus must be the same as the concentration of OH minus. Those two are the same. So let's then substitute this expression into here. Let's say that the OH minus concentration is the same as the H3O plus concentration. So therefore, we get that Kw is equal to the H3O plus concentration squared, okay, in pure water. So therefore, let's take the square root of both sides. The H3O plus concentration then is equal to the square root of Kw, which is equal to the square root of 1 times 10 to the minus 14, or 1.0 times 10 to the minus 14, keep those significant figures happy, and that is equal to 1.0 times 10 to the power of minus 7 mole per litre. So what we're saying is that in pure water, we've got a concentration of H3O plus of 1 times 10 to the power of minus 7 mole per litre. Right, we've just proven that. Now, again, an inconveniently small number. We've found that in quite a few videos. When we're talking about atomic or molecular scale things, that we end up with small numbers, and we use a variety of techniques to perhaps get around that. This is another case where we've got inconveniently small numbers. So let's get around that by taking the negative log of the H3O plus concentration, okay? And we are going to call the negative log of the H3O plus concentration a special name. We're going to call it pH, okay? pH is equal to the negative log to the base 10 of the H3O plus concentration. Okay, now, again, that's an equation that many of you probably have seen before. It is very important. It's worth a red box. That's one to learn. pH equals negative log H3O plus concentration. Now, any pitfalls here? Yep, the log, obviously. So again, looking at your calculator, you'll find that you've got two possible log buttons. You've got a log button that will either say log, or it will say log subscript 10. Those are the ones that we're using here. You may also have buttons that say log E or ln, natural log. These are yes, these are no, okay? So don't get your logs mixed up when you are doing these calculations. Okay, so pH is negative log of the H3O plus concentration. We've shown here that in pure water, the H3O plus concentration is 1 times 10 to the minus 7 mole per litre. So let's take the negative log of 1 times 10 to the minus 7. Okay, here's your exponent on your number is minus 7. Let's take the negative log of that, and we will find pH equals negative log of 1.0 times 10 to the minus 7 put that in your calculator, and if you don't get 7, then you've done something wrong, okay? So that then shows that in pure water, the pH is 7, provided that we are at a temperature of 25 degrees Celsius. Okay, that's an important point because the value of Kw changes with temperature. We saw that a few videos back when we were talking about the effect of temperature on equilibrium. Kw is an equilibrium, it will depend on temperature, or the value will depend on temperature, so therefore something to be aware of. Okay, pH equals negative log of H3O plus. How do we go the other way? Let's say we're given an H3O plus concentration, we want to calculate a pH. That's easy, we've just done that. We've plugged in this value and got a pH. What about the other way? What about we're given a pH and we want to calculate the H3O plus concentration? And this involves playing around with logs a little bit. It's simply a restatement of that above equation. The H3O plus concentration is equal to 10 to the power of the negative of the pH. And you might think, well, how are those two related? Well, quite simply, we're taking 10 to the power of x, basically. That's what we're doing to both sides here. And we end up with our expression for H3O plus is 10 to the power of the negative of the pH. And so again, we can do our water example. We know the pH of pure water is equal to 7. So therefore, in pure water, the H3O plus concentration is going to be 10 to the power of the negative of the pH. We said that the pH of pure water is 7. So therefore, the H3O plus concentration in pure water is 10 to the minus 7, or more correctly written, 1.0 times 10 to the power of minus 7 mole per litre. Okay, prepare to go both ways on those equations, okay? You need to be able to calculate a pH given an H3O plus concentration, and you need to be able to calculate an H3O plus concentration given the pH. The second one is probably a little bit more tricky, maybe, than the first one, but as I say, be prepared to use either. Okay. Boy, 10, 12 minutes has gone very fast. We've barely scratched the surface of the fundamentals of acids and bases, so we'd better continue this on in the next video. So that's where I'll see you. Take it easy.